每年至少来一次中国。他赞赏中国对基础科学的重视和科技进步，好奇心驱动求知欲。他说，这是人类探索未知世界不竭的动力。科学研究需要人才与交流，他希望摒弃纷争，加强国际合作。高端访谈专访诺贝尔物理学奖获得者、中国科学院外籍院士戴维·格罗斯，敬请收看。
关注国际焦点，洞察世界风云。大家好，欢迎来到本期的高端访谈，我是邹韵。本期节目我们来到了首届国际基础科学大会，这里云集了海内外顶尖的科学家们。而今天我们要对话其中一位，他就是诺贝尔物理学奖获得者戴维·格罗斯。他如何解读基础科学研究的魅力？如何展望物理学的未来？又如何看待中国科技发展迸发出的活力，以及跨国界、跨领域、跨学科合作所带来的智慧碰撞呢？今天我们一起在对话中寻找答案。
起飞，T0。
当前，新一轮科技革命和产业变革突飞猛进，学科交叉融合不断发展，科学研究范式发生深刻变革。基础研究成为人们理解世界、揭示自然、驱动科技进步、应对科技竞争的重要抓手。7月16日，首届国际基础科学大会在北京人民大会堂拉开帷幕，主题为聚焦基础科学，引领人类未来。包括10多位菲尔兹奖得主、图灵奖得主、诺贝尔奖得主以及50多名各国院士在内的300多名海外科学家及知名学者参加了大会。诺贝尔物理学奖得主、美国国家科学院院士、中国科学院外籍院士，现年83岁的戴维·格罗斯就是其中之一。
Professor Gross, great to have you with us on Leaders Talk. We're here at the International Congress of Basic Science. So this is the first top-level international congress of its kind hosted by China. So how do you understand the importance of basic scientific research? And what are the key messages that you're going to deliver here?
Well, I've been coming to China now for at least once a year, maybe, or maybe more, for 25 years now.
Right.
And one of the messages that I tried to convey early on was the importance of basic science. Scientists understand that really innovative applied sciences and new technologies can only emerge if you make progress on understanding the principles of nature, discovering new phenomena, and that's what we call basic science.
You have previously said that basic scientific research driven by curiosity lead innovation and can change the future. Exactly. What do you mean by that?
Let me put it this way. The motivation for most young people to go into science is that they're curious. They want to understand more. They want to discover new things. On the other hand, nature, the real world, is much better at posing questions than we are. And so the questions that nature poses are more interesting and more likely to lead to progress. And that's what I call curiosity-driven research. For example, the enormous development of tools that allow us to look inside the human body, MRI, CAT scans, all of those were direct consequences of purely curiosity-driven research. In the middle of the 20th century, people wanted to understand the properties, the magnetic properties of protons and nuclei. After these properties and developing instruments to study these properties, they realized they could do something that no one ever imagined. Or no one ever said, go find an instrument that could look inside your head or your heart. That was a product of new knowledge in answer to a question posed by nature and not by the Ministry of Science and Technology. China has realized that. There's this famous speech now I just read recently, President Xi, 10 years ago, on strategic thinking about science, which emphasizes the importance of basic science.
Exactly. As you mentioned, the Chinese government has made great emphasis on the importance of basic scientific research. And President Xi has also stressed that strengthening basic research is an imperative for higher level self-reliance and greater strength in science and technology. And it's the only path to building China into a world leader in science and technology. So how do you understand the significance of the vision proposed by President Xi?
Well, it's... I'm very delighted that he has expressed such views. 20 years ago in China and elsewhere in the developing world, there was a lot of debate. Should we spend money on basic science or on immediate problems? Because basic science is not cheap, and there are immediate needs. So there was a serious debate of, should we invest money in doing basic science, whose rewards will come many years from now. And we might let other countries develop that basic science. I think the argument has been won, and President Xi expresses the consensus now that basic science is absolutely essential, and China now is a very rich country, or on its way to become a very rich and powerful country, and so it should take a leadership role in basic science. And so I strongly commend that.
Many times in the past 25 years. So what are some of the major changes that you have observed taking place in the country in terms of basic scientific development?
Enormous. Every time I come back, I'm astonished at the visible changes, of course, with enormous construction and infrastructure, but also the enormous growth of the scientific community, the growth of the universities, the training, the number of young students who are anxious to do great science. And now China's gotten to the stage where it's able to create some of the world-leading and instruments and laboratories. In my field, they've made some very important discoveries. They have some of the biggest radio telescope in the world, and fast. They're marvelous.
Talking about international cooperation, which is greatly needed to address many of the complicated scientific problems, as the American scientist, what's your take on the impact of ongoing friction between China and the United States?
Oh boy, that's a tough question and very sensitive. I think what is happening is extremely tragic and harmful to both sides, to the world as a whole, very dangerous. It certainly, as far as its impact on science goes, it's really destructive. You know, nature is not easy. To unravel the secrets of nature requires a lot of very hard work, and it's expensive, and it requires the talents of as many people as possible. In the last few years, it seems to be moving in the reverse direction because of these frictions, politics, the rivalry of big countries. For science, this is extremely dangerous and bad. I'm very saddened by this.
This is not supposed to be a zero-sum game. It could be a win-win situation, right?
Of course. And the opposite is definitely a lose-lose situation.
戴维·格罗斯，2004年诺贝尔物理学奖获得者。他主要的研究领域包括量子场论、粒子物理和超弦理论。在普林斯顿大学任教期间，他和学生弗兰克·维尔切克发现量子色动力学中的渐进自由。这项夸克世界的精彩发现，对于粒子物理研究以及统一场理论探索至为关键，为构建万物理论铺下了一块重要的铺路石。由此，他们与休波利策共同分享了2004年度的诺贝尔物理学奖。 戴维·格罗斯教授经常来中国参与学术交流。他常说，科学研究就像一棵大树，树干和树根就是基础研究。只有重视基础研究，大树才有可能长出树叶，然后开花结果。
Professor Gross, you are a central figure in particle physics and string theory. Can you give the general public, like me, who may not have much knowledge about physics, about why these theories matter to understand the fundamental questions about the universe?
Some of the fundamental questions that we all ask as children and physicists have been asking for 2,000 years is, what is the world made out of? What are you made out of, ultimately? And we've been trying for centuries to understand how everything works. In the 20th century, great progress was made. In fact, the theory for which I won the Nobel Prize is 50 years old. And it explains how what the nucleus of atoms are made out of, what the proton, neutron, nuclei are made out of quarks, very strange particles that one has never seen because they're stuck, confined inside nuclei. Then there are more interesting questions that also mankind has asked for centuries. What is the history of the universe? How did it begin? How will it end? What is it made of? We try to answer those questions, and we've been quite successful, but some of the most interesting questions lie in front of us. And string theory is an approach to try to understand how gravity, the force, the universal force of gravity, combines with the atomic forces, with electricity and magnetism and nuclear forces together in a unified theory, which we still haven't discovered, don't understand yet. So physics is always on the road to new discoveries.
Right. As you mentioned before, it is like a gamble.
Any exploration is a gamble. You start off up the mountains no one has explored before. You don't know where you're going exactly, but you would like to get to the top.
Professor Gross, you won the Nobel Prize in Physics in 2004, and you have described that moment as in shock and haven't been able to get up the chair for quite a long time, with people keep calling for interviews. So how does it feel to be one day waking up and becoming a Nobel laureate, and what does it really take to make these great achievements?
Luck is certainly part of it.
Besides that?
You have to be born at the right time. So, discoveries in physics, some of my younger students complain that, I should have been born 5 years earlier or 10 years earlier. Well, it was not totally unanticipated. The prize came, in theoretical sciences, physics, it takes a long time to get a Nobel Prize. If you discover something in the laboratory, well, it's there, it's real.
Right.
Somebody else verifies it. But theory has to be tested by experiment, nature, and it can take a long time. And nature is the final judge. It's not like mathematics. In mathematics, mathematicians can decide that some theorem has really been proven. But in the case of physics or science in general, the only judge is nature. And nature never says yes.
Or no?
No, it says no, often,
no.
Most of the time. Well, so how do we test our ideas? We make predictions. We go out, we do better measurements, test our predictions. Nature, most of the time or often, says no. Doesn't tell you more information, just no. So we throw away them. Sometimes it says, so far, okay. Never says yes. They go to more experiments, more predictions. Some kind of fundamental science, it often takes a long time before nature has said so many times, so far, so good.
That's the best we can get.
We believe it.
Not 100% sure for
Never.
anything.
And every scientific truth, every scientific theory is inevitably going to be wrong. That's the history of science. Newton's theory of gravity is wrong. It was replaced by relativity. All of our old theories needed further modification. Not that they were wrong, they're still good approximations to the real world in certain limits. If I want to send a rocket to the moon, I don't use Einstein's theory. I don't need to. If you get close to the velocity of light, you have to use Einstein's theory. Einstein's theory is also probably wrong, we believe.
In some cases.
Near black holes, for example. There's incredibly massive objects that suck everything into them. We have no doubt that Einstein's theory breaks down. And one of the main lines of research now in fundamental basic physics is to understand how it breaks down, and so on. That's how science progresses.
Right. And you have once said that is like embarking on a mountain climbing trip without knowing where peak is,
in the fog.
But if you don't even know where the peak is, whether there's a peak, how can you make sure that you're always motivated?
Well, you're motivated because you want to know. So imagine you're on the mountain and you want to get to the top where you can see everything. So what do? And it's in the fog, so you can't see very far. Well, you go uphill, right? Makes sense. But sometimes you go uphill and you get to, you get to the top. It's not the real top. The real top is there. You have to go down and then up again by a different. That's sort of how it is. There are many false paths. Different people go in different directions. But if you have the desire to get to the top, which in this case means to understand what's going on, and you can test it. You get to the top and the fog dissipates, you can see that you're at the top. So that's a testing. It's a good analogy.
7月18日，在雁西湖畔，一场名为“物理之夜”的活动正在举行。这是首届国际基础科学大会500多场大会专题学术会议中的一个。中外学者在此交流，共享学术成果。物理之夜上，国际顶尖科学家与青年学者畅所欲言，碰撞思想，深入探讨基础科学领域的前沿成果，展望基础研究未来的发展方向。
Some of your students are renowned scientists. For instance, Frank Wilczek, who won the Nobel Prize with you together in 2004, and also Edward Wheaton, who is a recipient of the Fields Medal, and so on. And you've been working with so many young scientists now. So what would be your advice to those young scientists who are trying to make a difference in the fields of science, who are trying maybe one day also to win a Nobel?
Well, my way that I worked with students was to actually bring them into the collaboration, to work with me, which is different than the way some people treat their students. They give them a problem and the student goes off. And so that's not my style, because especially with students of this very high quality, it's great to have such collaborations, but I also think it's the only way to really teach students how to function at the highest level. We don't know how to teach people to be creative. We don't know how to teach people to have new ideas. We can only teach them by example. And so I think it's a good way to treat. First, my advice to young people is to start doing real research as soon as possible, because that's the only way you'll learn how to think and how to really do good scientific research.
Why do you believe it is important for students to ask the questions instead of answering them?
Well, the hardest part, that really is the secret of good science, the questions. When questions are asked in a precise way, then most of the work is done. It's really, the hardest part is to ask the right questions. to realize that, okay, well, maybe what everybody thinks is wrong. Maybe something should be a different way of looking at it. Once you have well-formulated questions, the answers will come.
The answers will come.
The questions are hardest. And that's why basic science is so important, because the questions that we ask in basic science are questions posed by nature, by the real world.
Well, for scientists, we believe that inspiration sometimes is very important, but you never know when and where it will strike. For Newton, right,
Yeah.
it's about apple falling off the apple tree. For Archimedes, it's about sitting in the bathtub. So we're curious to know, is there a defining moment of inspiration to you in this decades-long of
Yeah, it's
journey?
a little, well, it was easier in some sense for Archimedes and Newton because at that point very little was known, and the phenomena they were trying to understand were ordinary, everyday phenomena. We can see apples falling off trees. Our observation of what goes on at distances which are 1,000,000 billion times smaller than an apple require very special microscopes, big accelerators. It's harder to get direct intuition in the same way. Yeah, in some sense it was much easier back then. We could throw an apple up and see what happens. But now
It's
we
getting harder.
require thousands of colleagues who work on massive accelerators, and it takes them years and years. It's much harder, but we're getting closer to the essence of reality.
Well, let's talk a little bit about the cutting-edge technologies. Artificial intelligence is now becoming one of the leading ways of thinking worldwide.
Yeah.
So what impact do you think AI has brought to human society and also the surrounding, or the buzz surrounding ChatGPT?
Well, there's a lot of what we call hype.
Right.
Buzz. Well, artificial intelligence is very useful. You know, for example, you talk in Chinese, I can read a translation immediately. That's very useful. But, you know, it's very limited. The large learning machine model that have led to ChatGPT GPT have created a lot of hype, much more than I think is warranted. Those programs are kind of like they're optimization programs. They can very rapidly be trained to do very limited tasks. In the case of the large learning machines, what they're trained to do is to imitate human language by accessing an unbelievably large database of sentences. And I don't know whether you have played with that. They certainly have learned to lie. You ask them a question, they'll make up something which is consistent with kinds of things people have said over this incredibly large database, but it's often untrue, and they don't. So to call them intelligence is an enormous exaggeration.
You don't think it is
No.
that smart or wise?
They're good at doing certain things very well, like translation, sorting. They're very good at pattern recognition of human faces because they have a database with hundreds of or millions of billions of
Right.
photographs. Humans are still infinitely better at that, and although slower. And no, I'm not. I think it's incredibly overhyped. They've taught us remarkably very little about this remarkable computer, which is so much more powerful. They're not thinking like humans, and no, I'm not that impressed.
So you're not worried about that it's going to take your job as a
I am worried about
scientist?
humans destroying the world much more than about machines that they use, that they develop, that they construct, that they give the rules. We should worry about us.
Well, you have previously said that the three-body problem, the science fiction book, is one of the best that you've ever read in recent years. What is your impression and interpretation of the dark forest as well as the law depicted in the novel?
That was a very interesting idea. It, however, presumes, so the author...
刘慈欣, Mr. 刘慈欣.
Yeah, it's a remarkable book because he is a novelist, a science fiction writer. He can allow himself, he should, to stretch certain things to make an interesting book, thought experiment. And so some of the laws of nature he twists to make the book interesting allow for this kind of threat to from
outer space and different civilization.
Yeah, which, violates some of the laws we...
Right.
So, but it makes it interesting. It's a very interesting idea. We, of course, are sending out signals all the time. Doesn't worry me.
And the very last question we want to ask you is that at the age of 13, you have been very determined to become not only a scientist, but a theoretical physicist.
Right.
And after all those years of study and research in physics, what do you see are the biggest charm and beauty of this field?
Well, that, by the way, was driven not by any particular teacher or my parents, but rather by reading
A book.
Science books, popular science books.
Right.
And, but nowadays, kids, this can be very useful in a sense because it opens the door for a curious child to anything. I was reasonably good at mathematics. I liked mathematical puzzles. But these books were incredibly exciting because they taught me about the advances in our understanding of the universe and physics, and they also convinced me that thinking about these problems was much more interesting than artificial games and mathematical puzzles that were made by humans. These were puzzles posed by nature, and theoretical physics was a way to to explore solve those problems. And that's still what drives me, and it can be very rewarding to understand something that people didn't understand before, and to eventually for nature to say, okay, so far you understand me.
So far, so
Try
good.
harder, keep trying.
Right.
It's a lot of fun.
Okay, so Professor Gross, it was a great pleasure talking to you, and thank you so much for taking us into this adventure and exploration into the world of physics and science. That was really exciting. Thank you so much.
It was a great list of questions. I was very impressed.
在采访当中，格罗斯教授表示，中国科技的飞速发展给他留下了深刻的印象。他激励当代青年要保有一颗好奇心和对科学探索的热情。海纳百川，有容乃大。对于未来，他希望各国各学科之间拓宽创新之路，开展互利共赢的国际合作。感谢您收看本期的高端访谈，我是邹韵，我们下期再会。